So, all right. So we'll start off by looking at some of the forces that are involved in your ankle joint. Okay. So what we're going to see is, what we're going to look at is, suppose a woman or a man stands on one foot on tiptoe. So let's say you're standing like so, and we'll look at what are the forces that are involved. Okay. So if you're standing on one foot, here's your weight, which is denoted by mg, and that is being balanced by this force. So that force is equal to mg. M is your mass, g is the acceleration due to gravity, and that's your weight. Okay? So now you're balanced. So let's see what happens. This bone is exerting that force on the ankle, and here's the tension in the tendon. Okay, so if this is the pivot point, okay, so you're balanced, your toe is off the ground. This force is trying to turn your ankle clockwise. This force in the tendon is trying to turn your ankle counterclockwise. And if your ankle is at rest, then this torque must balance that torque. Okay? All right. So let's say this angle is theta. This angle will be theta, and this angle will be theta. Okay. Again, you can figure it out from geometry. All right. So what it is the clockwise torque is balancing the counterclockwise torque, and there are signs to that, but I'm just going to write the magnitude. So this force on the ankle, the force on the ankle times cosine theta times 15, this is the moment arm, should equal the force on the tendon times cosine theta, that's the component of the force, and then this would be the moment arm. Okay. Cosine theta times 20. Okay. Cosine theta cancels, and so the force on the ankle is force on the tendon times 20 over 15 equal to 4 over 3 times 4 over 3. All right, so that's how you figure out forces. But now let's, okay, so again, the force on the toes is equal to the force that's on the floor exerted by the person, which is mg. Okay, here's the force. Okay, now, so what we'll do is we'll first calculate the force on the tendon. What I've shown you here is the force on the ankle related to the tendon. The force on the ankle is 4/3 the force on the tendon. Okay, let's calculate the force on the tendon. Okay, so in this diagram, here's the force on the toe that is trying to turn the ankle. So now we'll calculate everything about this pivot point. This force is trying to turn the ankle clockwise. The force on the tendon is trying to turn the ankle counterclockwise. So this torque is being balanced by this torque. And that's what we've written here. Okay, so again, so this angle is theta in this diagram. So in this calculation, this angle is theta. And there's the moment arm. Okay, we're going to calculate the torque about that point. So the force on the toe times cosine theta, that's the component of the force, times 15 is the moment arm. Okay. And this force, again, this angle is theta. Okay. So tendon force times cosine theta, tendon force times cosine theta, times the moment arm, this is 5 centimeters. All right, so here, this is pretty amazing number. So the cosine theta cancels. The force on the tendon is 3 times the force on the toe, which is just the weight, just your weight. So when you stand on tippy toe on one foot, the force on your Achilles tendon is 3 times your body weight. Okay, that's what that says. Okay, and we calculated in the previous problem, the ankle force is 4/3 the tendon force. So if you do that, so again, let me do this. So the force on your tendon is 3 times your body weight, and the force on the ankle, here it's called the joint force, is 4/3 times the force on the tendon, which is 4 times your body weight. Okay, absolutely amazing. Okay, so you stand on your tippy toe on one leg. This force on the ankle bone is 4 times your body weight, and this force is 3 times your body weight. Okay? So when you stand on tippy toe on one foot, the force on your tendon is 3 times your body weight, and that on your joint is 4 times your body weight. Okay, when you hop on one foot, the forces are even larger. Okay. What's that? Yeah, so we'll come to that in a second. So the thing is, so when you stand on one foot, we'll calculate what are the forces, and when you run, the impact of the ground stopping you, so you had a velocity, your foot had to be stopped, it's 7 times your body weight. So, all right. So the message is, your muscles can exert large forces compared to your body weight. Okay, so now we'll look at this situation. Here you're lifting a weight. Okay, now we'll just talk about a weight being lifted here, so you can think of a bowling ball you're holding. Okay, so right now this is a barbell that is shown. So in weightlifting, while lifting heavy loads, holding the body in steady equilibrium requires muscle forces that are quite large. Okay? So this is a record lift or in the range of 110 kg. 110 kg is roughly 1.5%. So in this world event, you hold this lift like that and just lift it like this. So the record is 1.5 times a person's body weight. Okay. Now I'll show you the numbers just on, let's say, lifting a bowling ball. Okay, so you're holding a bowling ball like this. Okay, so here's this weight. There's the joint. There's the pivot point. Okay, so this weight is what it's trying to do is it's trying to rotate this bone clockwise. What is preventing this bone from rotating clockwise? This force in the muscle is turning this bone counterclockwise, is exerting a counterclockwise torque. So if you're holding something like that, this torque is being balanced by that torque. All right, so let's look at that now. So let's say this is the load. We'll call this a load. Okay. So this is the load. The torque of this load is this force times the moment arm. So the load times the moment arm. Okay. And since it's a clockwise torque, that's given negative. It's a negative, which is being balanced by the force on the tendon times this moment arm. That is rotating the bone counterclockwise, so that's a positive torque. The force on the tendon times 4. Okay. So if you bring this term to that side, 35 divided by 4 is 9, roughly 9. So the force on the tendon is 9 times the force on the load. So what this is saying is, again, absolutely amazing. You're holding, let's say you hold a 20-pound bowling ball like that. The force on your tendon is 180 pounds. 9 times that. Okay? All right. The mechanical advantage of a machine is how much you can lift up, the force on the load, divided by the input force. That's a mechanical advantage. Okay. generally what we want to be able to do is we want to be able to lift heavy loads with small forces. But here, and then the mechanical advantage is greater than 1, if mechanical advantage is greater than 1. So mechanical advantage is output force, what you're trying to do, divided by what you have to input. Okay. Here, the mechanical advantage is a tenth. You're having to input a force 10 times as great as the output force. And again, we've seen this many times before in our body's design. Why is that? That's because the muscles cannot so work in is equal to work out. What you get out is equal to what you put in. And what you put in is input force times input distance is output force times output distance. Okay. So since you can only contract the muscles a small amount, the input distance is small, the contraction, you are willing to put in large forces because your muscles can contract only a small amount. Okay. All right, so the mechanical advantage is that is a tenth. All right, so here is a technique to lift heavy loads. Okay, so let me draw this diagram back again. So there's your arm, there's your tendon, the force that the tendon applies. Okay, you saw that if you're lifting a bowling ball and the bowling ball is there. Okay, so what is the equation? This is the, I'll call this input distance, and this is the load or the output force, and this is the output distance. That's the moment arm. So what you saw was input distance, input force times input distance is output force times output distance. All right, this is the maximum force that your tendon can bear. And this input distance is fixed. Okay, so this number is fixed. So if you want to lift a heavy load, what is it that you need to do? I'm sorry? If you want to increase this, you have to decrease that. So the heavier the load you want to lift, the closer it needs to be to the tendon. And that's what's demonstrated here. See, these guys are lifting this heavy load, and how are they doing that? See, the load is effectively acting there. Okay, so the force of this load is acting here. Yep. So let's say this was 40 centimeters, and you're able to lift 20 pounds. If you come to 4 centimeters, you'll be able to lift 10 times as great a load. Okay. If you decrease this distance by a factor of 5, you can lift a 5 times heavier load. Okay. So here's a technique for lifting heavy loads. Okay. Did you guys understand that? Has anybody seen this, something like this? You have? What's that? All right. What's that? You use it a lot?
I've moved many times over these.
Okay.
Carrying a mattress or something stupid.
Mm-hmm.
You just walk and it's just there.
No. Oh, so now you understand. Mm-hmm. All right, so again, we are showing you some of the large forces that are involved in your body. Okay, so here's another large force. Okay. So when you chew, this is a masseter muscle. Okay, this is what contracts, and so so your upper jaw is immobile. It's the lower jaw that moves. Okay, so it raises the lower jaw. There is the pivot point. Okay, so this muscle is turning the lower jaw in that clockwise direction, and when the lower jaw pushes against the upper jaw, this molar applies a force on the lower molar. Okay. So when this hits the upper jaw pushes back on the lower jaw. And these forces are easily measured. So when you go to a dentist, they'll put a force sensor between your teeth, and this force can be measured. And so the measurement shows that this force can be as large as 1200 newtons. Do you guys have any idea what that number is? That's twice your body weight. So the force that the upper jaw can exert on this molar is twice your body weight. Okay, why did we evolve that way? Well, because the force, it helps you grinding food with your molars and stuff like that. Okay? So you need large forces. Okay. Now here's the deal. See, the gap is not too large. You can get large forces, but you can't put large objects in the molar. Okay. So the force can be large, but there's a trade-off though. You may be capable of great bite strength, but your jaw is limited range of motion. Okay, and so you have limited bite speed. You can't close your mouth too fast. Okay, so you have limited bite speed. Okay. Now, what this number tells you is the following. If this is 5 centimeter, this moment arm here is 7 centimeters. Okay, so this is a clockwise torque, so force of the muscle times 7 centimeter, which is minus because it's a clockwise torque, and this is a counterclockwise torque. Force of the bite times 5 centimeter equal to 0. So the bite force equal to, oh no, this is 5 centimeter. Okay, so the bite force is 5/7 the muscle force. Okay. And we saw that muscles can exert large forces, so the bite force is large here. Okay. Now, if you increase this distance, if this distance increases, this distance will increase, the bite force will become smaller. Okay, so if this didn't, so the bite force on these teeth is smaller. All right, here's what happens in dogs and cats. Their jaw is much bigger, and so that force is much further. So the force that this canine can exert is much smaller in a dog or cat. Okay. So the canine teeth, dogs and other predators have different needs. Okay, so why did they evolve this way? Okay, the force is smaller, but what they want is a larger gap to close. Okay, so they can close their jaws faster. Okay, and get at somebody's jugular. Okay. Their canine have a wide range of motion. Dogs and cats can open their mouths much wider than we can, and are well adapted for rapid slashing bites. Of course, what did they give up? The bite force is smaller. The smaller bite force is compensated for teeth that are much sharper than ours, so they have to maintain sharp teeth. Okay. So, you can send off a cat in the wild, take off its canine, and they're in trouble. All right, so we saw that forces that in your body can be large. So now we'll look at elasticity and deformation. Okay. No object is perfectly rigid. Real objects undergo deformation in response to applied forces. So if you have let's say you have a tendon, you apply a force like that, what will happen? It will stretch. Okay. The softer the material, the more it'll stretch. For instance, a rubber band would stretch more than a steel bar, and so on. Metals are stiffer, okay? But everything stretches. And what will happen when you let go of the force? What will happen when you let go of the force?
Tracks.
I'm sorry?
Tracks.
Yeah, it goes back to its original shape. How many times will it do that? So in a bridge, if you have a suspension bridge, if you have a suspension bridge, this road is suspended by cables. You have a car that goes by. When the car is on the bridge, the cables stretch, and once the car goes by, you want the cable to go back to its original shape. How many times do you want to do that? Millions of times. Okay? You don't want the cables developing cracks and stuff like that. Same thing with your body, A tendon stretches, you remove the force, the tendon needs to go back to its original shape all your life. You want a lifetime warranty on things, right? All right, so real objects undergo deformation in response to applied forces, and when you remove the applied force, the deformation needs to go back to zero. Okay. Most biological materials deform considerably more than metals when subject to forces. Okay. So for biological structures to accomplish their functions are determined by not only their biomedical properties, but also their mechanical properties. So a lot of our functions depend on the mechanical properties as well. Your arteries flex with the pressure of each heartbeat. Okay, if your arteries become too stiff, then your heart will have to work harder. Okay, and here's something that has to work all your life. And if it has to work harder, it's not good for it. Again, both bones withstand impact and deform in the process. So when you run, your bones compress. Okay, and we'll show you how much your bone will compress when you run. Okay. So nearly all biomaterials are elastic. We call a material elastic when if you remove the force, it goes back to its original shape. If it doesn't go back to its original shape, then it's not elastic. Can you think of an example which is not elastic? You can take dough, pizza dough, you stretch it, and then it doesn't go back to its original shape. Okay? Nearly all biomaterials are elastic. They deform in response to applied forces. By the way, deformation is often functional, storing energy for later use. So tendons stretch and they store energy, and that energy can be used later. Okay. So here is in muscles. Here is the fundamental thing that stretches and contracts. Okay. So actin and myosin. Okay. So here is so here is the actin filament, and here is the myosin. So myosin acts as the molecular motor. Okay, so myosin is the motor that helps in the compression, using energy from ATP to pull actin filaments. So this myosin uses energy from ATP, and what it does is it compresses this spring. You see that spring is compressed, and it's pulled the actin filament closer. Okay, so there is the basic mechanism for muscle contraction. Okay, so a myosin molecule uses energy from ATP molecules to compress the spring, you can think of it, and then it brings this actin filaments closer together. You see in this configuration, there's the gap, and here's the compressed structure. Okay, and you can see the compression is very small, and that's why they have to. So remember, input work is force input times distance input. Since muscles can contract only small distances, they have to adapt. They have to be able to apply large forces. Okay. All right, now we'll look at stress and strain. So we'll define two terms in relation to elasticity. Okay, so here's a rod, here's a metal rod. You apply a force like that, and the rod stretches. When you remove this force, as long as this material is elastic, this stretch will go back, the rod will go back to its original shape. Okay, and what this shows you is, okay, If you apply this much force, and this force is in kilonewtons, that's the amount of stretch, okay? So the greater the force, the greater the stretch, okay? And this is a linear relationship for small forces, meaning you double the force, the stretch will double. So for 5 kilonewtons, there's the stretch, and for 10 kilonewtons, the stretch is twice as much. Okay, so this is a linear relationship. Okay, this is shown as data for the force needed to stretch a 1 centimeter diameter. 1 centimeter diameter is about this thick steel rod. Okay, 1 centimeter is a little less than half an inch. And 1 meter long steel rod. So steel rod 1 meter long, about this long. It's about half an inch thick. Okay, and this number shows you what this number shows you is it takes a large force, 16,000 newtons, to stretch the rod by 1 millimeter. So to stretch a steel rod 1 millimeter is that much, tiny amount. It takes 16,000 newtons. That is equal to the weight of, let's say, 1,000 newton is 1.5%, not 2%. About 30 people. 30 people hanging onto the rod will stretch it 1 millimeter. Okay, that's how stiff steel is. It's hard to stretch steel. Okay, so you saw that the force needed to apply and the stretch are linearly related. Okay, the force and the stretch are linearly related. This is sort of the spring constant of the material. Okay, and stiffer the material, bigger that number is. Okay, so bigger that number is. So stiffer the material, bigger that number, and the slope is bigger. Okay, so softer materials will have smaller slopes. Rubber band will have smaller slopes. Okay, and so we'll see in our body there are some materials whose slope is smaller to begin with. So you've taken a rubber band, you stretch a rubber band. Initially, it will stretch easily, and then after a point, what will happen? It's harder to stretch it, rubber band. Okay, so it becomes stiffer. Okay? So that means its spring constant changes. Okay, and let me show you. So here, see, here's rubber band. Initially, there's the spring constant. Up to that point, it's stretching easily, and then it becomes harder to stretch. Okay, so its spring constant will increase. All right. Objects with small k are called pliant. Okay. Rigid objects have larger values of k. They're difficult to stretch. An object with small k is easily stretched. Okay. So here is this is the spring constant of the material. Okay. Now this number depends on the dimensions of the object. Okay. So what we want to do is get a number related to this, except that it doesn't depend on the dimensions of the material. Okay. So if you do the following, if you take the force and divide it by the cross section of the rod, force divided by cross section, and then if you take the length, the stretch divided by the length, the stretch divided by the length, now this number is called the Young's modulus, and it only depends on the material. It doesn't depend on the dimensions of the rod. Okay. So this is called the Young's modulus, and it's related to this guy. It tells you the stiffer the material, bigger this number is. Okay. All right. This guy is called stress. Okay, so that's the force you're applying per unit area of cross section. And this guy is called the strain, how much the material deforms. Okay, so the greater the stress, the greater the deformation, greater the strain. Okay, and that's the Young's modulus. And again, larger the Young's modulus, stiffer the material. Okay, smaller the Young's modulus, softer the material. Okay. Large values of Y characterize materials that are stiff and rigid. Softer materials have the same smaller value of Y. Okay, smaller values of y. In general, biomaterials are softer than metals, okay, as you would guess. Okay, so here are the Young's modulus. For steel, again, this is given in millions of Newton per meter square. Steel has 200,000 times that. There's copper, this is metal, and there's bone. Okay, so that's about 20,000. So bone is 10 times less stiffer than steel. Okay, has Young's modulus 10 times smaller. The spider silk is 20 times softer. So spider silk is 20 times softer. So what that means is if you apply the same stress to spider silk and to steel, spider silk will stretch 20 times more than steel. That's what that number means. But look at this tensile strength. Tensile strength is the same. Tensile strength is the force needed to break a silk and a steel rod of the same cross section. So silk, spider silk, while it's more pliant, you need the same force to break it. Okay? So you might have heard that is spider web as strong as steel, and it is. Okay. All right. So we'll come more to that. Okay. So now here's another kind of force deformation that you will experience. Okay. So if you apply two parallel forces like these are called shearing forces, and this is the kind of deformation that happens. Okay. So this upper layer is shifted compared to this lower layer. Okay. And the shear modulus denoted by S, again, this is the stress, okay, the force divided by the surface area, and the strain is this deformation divided by how far apart they are. Okay? So that's how you measure shear strain. And this is the shear modulus. Bigger this number, less deformation you'll have. Okay, so when you bend over and lift something like that, your discs are subjected to force like this, shearing forces, and your disc will deform like that. Okay, and you can cause damage to your disc. Okay, so when you remove this force, what you want the disc to go back to your original shape. What are the discs doing? They're the shock absorbers between your vertebrae. Okay. All right, so shear forces happen when we bend over and lift objects. Spinal muscles need to respond to prevent vertebrae sliding towards one another. Okay. The discs they experience compressive forces when you lift an object like that. Okay. Compressive forces press the vertebrae and the intervertebral disc commonly when we sit. So when you're sitting, your discs are compressed. Okay, and so on. Here's another force that your discs have to bear when you're playing sport. If the upper body turns more than the lower body, so then this disc is rotating relative to this disc, and you're experiencing torsional forces on your disc. Okay. Again, you experience all these forces, and what is it that you're concerned about? No damage is caused to body parts, and you want, when the forces are removed, you want the body parts to go back to its original shape. Okay. And how long do you want this to happen? I'm sorry? Every time. All your life. Okay. So you need to build structures that can withstand these forces, and when you remove those stresses, you want them to go back to their original shape. Of course, there are limits to the forces that you can bear, and if you cross the limits, then you cause damage. You break bones, you tear tendons, and so on. Yeah. All right, so now we'll talk about the elastic limit. So what happens if the forces exceed the limits. Okay, so what this graph tells you is, again, stress is how much force you're applying per area. Strain is the amount of deformation per unit length. Okay, so this is in the linear portion. What this is telling you is in the linear portion, this is the elastic region. The elastic region is up to there. So when you remove the stress, the object will go back to its original shape. This is the linear region. If you double the stress in this region, the strain doubles. If you double the force, the stretch will double. Okay, so this is the linear region. You can apply forces up to that point, and if you remove the force, the object will go back. What if you apply forces greater than that? You permanently deform the object. That's what that is saying. And this is the breaking point. If you apply a stress that large, that object will break. Okay? So that's what this graph tells you. So for rubber, here's the linear region, and after a certain point of stretching, it gets stiffer. It takes greater force to stretch it. Here, you've permanently deformed it, and that is the breaking point for rubber. Okay? So that's what those graphs tell you. Any material will break if you pull too hard. The tensile stress that causes a material to rupture is called the tensile strength. That's the tensile strength of that material. That is the force that's needed to break it. Okay? And we saw that in this table, the tensile strength of structural steel, okay, in units of 1,000,000 Newton per meter, is the same as for spider silk. Okay? So if you take a spider silk and you take a steel fiber of the same cross-sectional area, okay, and same length, the force needed to break it is the same. What is the difference between silk and steel? Steel is much stiffer, so steel doesn't stretch easily. Silk will stretch easily. Okay? But the ultimate strength is the same. Okay? So that's what those numbers tell you. Okay? So elastic limit when a curve for steel and rubber. So what are the difference? See, for a given stress, steel doesn't stretch as much, and rubber stretches much more. Again, like I said, the lower the slope, the smaller the slope, the less stiff the material. Higher the slope, more stiff the material is. And for tungsten, the slope will be even higher. Tungsten is stiffer than steel. Okay? Okay, so why does rubber stretch more? So rubber is a polymer. In its relaxed state, the long chain molecules are folded and coiled with only hydrogen bonds holding the polymers together. So you can think of the molecular structure of rubber as coiled springs with hydrogen bonds holding them. And so when you're stretching the rubber, initially all you're doing is breaking these weak bonds, and it stretches easily. But once you've stretched all these coils, then you try to stretch it more, then you have to stretch stronger bonds, and so the rubber gets stiffer. Okay? So that's what's happening. Okay? So in the relaxed state, the long chain molecules are folded and coiled with only hydrogen bonds holding the polymer in the folded configuration. When you begin to stretch rubber, you are unfolding and uncoiling the polymers. Hydrogen bonds are weaker, so it takes less energy to break them. Okay? Consequently, rubber is very pliant. Okay. Once the polymer is uncoiled, further stretching requires lengthening carbon-carbon bonds, and this is much more difficult, so it gets stiffer. Okay, rubber gets stiffer. Many biomaterials are polymers, and hence their mechanical properties are more like rubber than steel. Okay, so a lot of biomaterials, you can stretch them. Initially, you can stretch them easily, and then it gets harder to stretch them. So your arteries are designed like that. Okay, so when your heart pumps, initially they'll stretch easily to accommodate blood flow, but they don't want to stretch too much because that can be an aneurysm and it can burst the blood vessels. So initially you want to be able to stretch easily, but then you need to get stiffer. Okay, so how do you design such things? And we'll see that toward the end of the chapter. Okay, so you want it's like if you have you've all filled water balloons. If a water balloon, if it stretches, you keep filling it and it's still soft. When you filled it, it'll burst easily. Okay, so what you want is the water balloon to get stiffer, so not to burst. Okay. So biological materials, especially they have long fibers, and they're more complex than metals. Okay, so a tree, for instance, if you stretch it along this direction, that's harder to break. But if you try and bend it, then that's easier to do. Okay, so in many cases, their mechanical property depends on whether forces are applied along or perpendicular to the fiber direction. Okay, so it's harder to stretch a tree like that, but it's easier to bend it like that. Okay. So a plant stem is strong along the axis of the stem due to the cellulose fibers, but has little resistance to bending or kinking. So here's the spider silk. Here's the breaking point for steel, and here's the breaking point for spider silk. You see the breaking point are the same. Okay, so this is the stress, and that is the strain. Okay, so that's what we saw, and that's the number that you saw here. Okay, that's the tensile strength you saw. Is the same for structural steel and the spider silk. Okay, so the breaking point is the same. But here's the difference. Okay, for this breaking point, the strain is 1. What that means is strain is the stretch divided by L. The stretch divided by the original length. So the spider silk, when it's reached its breaking point, its length has doubled. So if you had a 1-foot spider silk, it's become 2 foot by the time it's ready to break. Whereas steel, its length has increased by only about 1%. So if you take a 1 meter steel rod, it's stretched by about 1 centimeter when it's ready to break. Okay, so that's what that means. Yeah. So suppose we take equal lengths of steel wire and dragline silk of equal cross section and slowly stretch them and measure the force and displacement of each unit until it breaks. The graph shows the resulting, so the graph is for this condition. Okay. And by the way, Young's modulus, so Young's modulus for silk is 20 times smaller, meaning for a given stress, if the steel rod stretches 1 millimeter, the silk rod will stretch 20 millimeters for the same force. Okay? So the steel we're talking about is structural steel. There are high tensile steel that are 3 times stronger, but they're specialized steel. Yeah, so you have these, and they're more expensive to make, and they're used for specialized applications. Okay? But here's the amazing part. To make steel, what do you have to do? You have to heat it to high temperatures, anneal it, and all that. You have to heat it to thousands of degrees Celsius. Here you're making silk. Where are you making the silk? Inside an insect's body, at room temperature, at body temperature. So you're making this material. Here's a natural product made at room temperatures by spiders digesting small insects. And here's a process, you're making something as strong as steel, which is made at high temperatures and annealed. So it's pretty amazing. Yeah. We'll talk about loading and unloading curves. Okay, Okay, this is stress. Again, stress is force per unit area. Okay, and this is strain, which is stretch divided by L. Okay, now I'll draw it for a spring. Okay, so if you apply a force to this spring, it will stretch. Okay, and for a spring, the curve is like that. Okay, force versus stretch. Okay, so for an ideal spring, it goes straight like that. And then as you remove the force, the spring will come right back. Okay, now what in this diagram, this area, the area under this curve, this area is the energy stored in the spring. Okay, so when you stretch the spring and you remove the force and it stretches back, all the energy is given back. Okay, so here, so the loading curve and the unloading curve are the same, identical for the spring. But for silk, here's the loading curve is like that, and then as you remove the stretch, the silk is not coming back to its original length. There's a memory, and the unloading curve is, eventually it comes back to its original length. So the unloading curve is like this. Okay, what that means is the energy stored is that much, and when it's coming back, only this much energy is given back. So it's not giving back all its energy. And that's a good thing. Remember, the spider wanted that. Why did the spider want that? Because when a bug hits the spider web, okay, if the spider web gave back all its energy, it would just fling back the bug. You don't want to fling back the bug. You don't want to give all that energy back. Okay, the web will bounce a little. Okay, and it turns out this area is only about 35% of that area. So you're giving back only 35% of the energy, which is making the web bounce, but it's not throwing away the bug. Okay. So the graph shows the response of silk as the stress is increased and then reduced. So when you're increasing the stress, the silk fiber is stretching, and then as you're removing the stress, it comes back along this curve. So this is a loading curve, this is unloading curve. This is the energy stored, and this is the energy given back. What happens to the rest of the energy? What happens to this energy? It turns into heat. Okay? When stress is first reduced after reaching maximum, there's very little reduction in strain, meaning the stretch has not gone down at all. This is a silk, that is, a silk fiber initially retains its full elongation even though the pulling force is decreasing. This fiber snaps back only after the stress has been significantly reduced. So, and then it snaps back. Many biological materials behave similarly. Okay. A stretch spring stores energy. Okay, so if you stretch a spring this much, it has stored this much energy. Okay, so if you stretch a spring, so this is the unstretched length, and if you stretch it to that much, this is the force and the stretch. If you stretch it by that much, this is the stored energy. So when you stretch a silk fiber, the area under that curve is the stored energy. And when you unload it, it's giving out only this much energy. Okay? The fact that silk's unloading curve falls below its loading curve means that the energy stored while stretching is not all returned upon contraction. Much of the stretching energy is converted to heat, thermal energy, and raises the temperature of the skin. Okay? The energy released when contracting is equal to the area under the unloading curve. So this area is what is the energy released. Okay? The fraction of energy that is returned is called the material's resilience. Okay, so spider silk, okay, this is the energy released, and this is the energy stored. Spider silk has a resilience of 0.35, meaning only 35% of the energy stored when silk stretches is returned as it contracts. So spider silk has a resilience of 30.35. What is the resilience of tendons? 0.9. Remember, tendons give up 90% of their energy. That's why kangaroos can. What is the resilience of a spring, an ideal spring? 1, because it gives back all its energy. Okay? A spider web must dissipate the energy of a flying insect, not store up the energy and then fling the insect back like a trampoline. Okay? So some biological structures need to store and then release energy. Others, such as spider web, need to dissipate energy. So organisms have evolved biomaterials that suit their function. So, so if you want to dissipate energy, then the loading curve needs to be like that. Okay? If you want to return all the energy, the unloading curve of a tendon is almost the same as the loading curve. Okay? So the unloading curve for a tendon will look something like that. All right, so here is the structure of artery. So here's a cross-section of an artery wall. Okay, so you see these are collagen fibers. And the collagen fiber are in an elastin, in elastin. Okay, so the collagen fiber are in this, the pink stuff is elastin. Okay, the pink stuff, elastin is soft, it'll just stretch like rubber. These collagen fiber, once they're straightened out, they become stiff. All right, so here's an artery. So here's the design. Initially, it'll stretch easily because the elastin material stretches easily, and the collagen fiber is crumpled, and so till it straightens out, it doesn't take large forces to straighten out. But once it's straightened out, now it's harder to stretch the collagen fiber. So once the arteries is stretched to a certain extent, it's harder to stretch it to a larger, to stretch it more. Okay? And that'll prevent an aneurysm and prevent a blood vessel from bursting. So that's the design. Okay? So your arteries, your blood vessels use two different materials to initially make it softer and then make it stiffer. Okay, so remember the curve, the force versus stretch. Initially you want to make it softer, and then after it's stretched to a certain point, you want to make the artery stiffer. Okay, and this is how you do it. So you use two materials, collagen and elastin. If arteries were very stiff, you would experience a surge of pressure each time your heart beat. Arteriosclerosis is accompanied by an increase in systolic blood pressure. So arteriosclerosis is a hardening of your arteries, and the pressure is increasing. So the systolic pressure is the larger of the blood pressure. So when you go to a doctor's office and they say 120/70, 120 is the systolic blood pressure. Arteries need to be soft and elastic so they can expand with each heartbeat. When they're soft and they expand easily, your heart doesn't have to pump as hard. Okay? At the same time, an artery cannot be too elastic without having an increased risk of aneurysm. Okay, so what we are saying is, initially you want the arteries to be soft and pliant, and then after a certain amount of stretch, you want them to become stiffer. Okay? So artery walls have a complex structure. Their mechanical properties can be understood by modeling them as a composite of proteins, elastin and collagen. Elastin is soft. Collagen, once it gets stretched, it becomes stiff. Okay? Collagen occurs in almost pure form in tendons. Another anchor, it is stiff, strong fibrous material with a resilience of 0.9. So collagen has a resilience of 0.9. What does that number 0.9 mean? If you stretch collagen, the energy stored, 90% of that is given back. Okay, that's what that number means. That's what the tendons in kangaroos. Okay. Elastin is the body's rubber. It's soft, pliant, easily stretched material. Okay. So when the artery wall is relaxed, collagen is kinked up. Okay, coiled collagen. It's kinked and coiled collagen fibers are embedded in the soft elastin matrix, and so when the blood is pumped, the arteries stretch. The elastin materials, that underlying elastin material, stretches easily, but once the collagen fibers have straightened out, now the arteries become stiffer. Okay, so then it becomes harder to stretch the artery, preventing aneurysms. Okay. All right, now let's look at your bones. Your bones are structured like this, so they're sort of cylindrical. Okay, and they have a wall that is stiff, and inside the central material is spongy. So here's the inside of here's a cross section of a bone, and this material is dense. This is like sponge. This is where all the physiological functions go, and this is the mechanical functions. Okay, so this is the load bearing, and this is where you make blood vessels and all that kind of stuff. Okay. So the spongy bone serves essential physiological functions, but contributes nothing to the bone's mechanical properties. So this doesn't support any weight. The mechanical properties of the bone can be modeled as those of a hollow cylinder of compact bone. So this guy is what supports all the mechanical properties. So we are interested in mechanical properties, and you can just model this as a pipe with thick walls. Okay, so that's what we're going to model the bone as. Okay, it turns out that the bone, so here's the bone. Okay, so let me do a. So here is a. Okay, now let's say I apply a 1,000-pound force to the bone like that, and I apply a 1,000-pound force to the bone like this. This is called a compressive force, and this is called a tensile force. When you try and stretch the bone, it's a tensile force. This is a compressive force. Okay, the forces are equal. When is the bone more likely to break? Tensile force. Okay, the bone is stronger under compressive forces. The bone is weaker under tensile forces. Okay, so the tensile strength is smaller than the compressive strength. Okay, what does that mean? So for instance, here's how bones break. So if this is your bone, if you apply a force sideways, force like this, you can see that this part of the bone stretches, and this part of the bone is compressing. So the bone is stronger under compressive forces and weaker under tensile forces. So when you apply a force like this, the bone will crack here. Okay, so you guys have stretched a rubber band. When the rubber band breaks, what happens to all the energy that was stored in the stretching? It's released, and that broken part will come and hurt you. Okay, so just like that, when the bone cracks, all that energy is released, and the crack will propagate. Okay, so that's how you break a bone. Okay, so if a bone is bent far enough, it will fail on the outside edge when the stress at the outside edge reaches the tensile strength. The energy released when the stressed bone breaks then drives a crack. A bone will fracture well into or even through the bone. Okay, so that energy released propagates the crack. Okay, now we'll show you some numbers. By the way, I've added some slides, so you might have to look at the latest slide. I will upload these edits as soon as I get to my office. Okay, so I made changes last night. Okay, so here's what we're going to look at. We're going to look at some numbers. So do you risk breaking a leg during normal activities of running and jumping? Of course not. To find out, so let's look at some numbers. We'll look at an adult human femur. So the femur can be modeled as a long hollow cylinder. So here's the cylinder. So if you want to make a bone weaker, what do you have to do? How can you make a bone weaker? Okay. Okay. So what would you have to reduce to make this bone weaker? How could you make this bone weaker? If the walls become thinner. That's what happens in osteoporosis. Okay? So, so here's the amazing part about bones. We'll talk about this. So let's say you have a bridge. The bridge is supported, those spans are supported by columns of concrete, right? The bridge. If cracks have developed in the concrete, can you go remove that much portion of the column and patch it up? You can't do that. Your bones are constantly being reprocessed to maintain their strength. So your bones are constantly being, it's like every crack is being fixed all the time. They're amazing. Okay, so we'll come to that. All right, so let's look at this. So the compressive strength of a compact bone is that much. The compressive strength meaning how much force you have to apply, compressive force before they break. Somewhat greater than the tensile strength. Okay, so now we'll look at an 85 kg man and 190 pound man stands on one leg. So we're looking at a 190 pound fellow standing on one leg. And what we're going to look at is so the bone compresses, and we will look at how much the compressive strength is. Okay, so this gives you the area of that thing. I'm not going to go through the details. So this gives you the area of that, the bone. The stress is the weight of the person divided by that area. Okay, and that is that much. And here is the compressive stress of the bone. So if you divide that by that, it gives you 1.4%. Okay, so when you're standing like this, all you're doing is the compressive stress is only about 1% needed to break it. So you have plenty of room. Okay? If you're running, the compressive forces increase by a factor of 7. So 7 times that, that's 10%. So even when you're running, the compressive forces you reach only about 10% that of what's needed to break. Okay? So that's what that number is. The strain is for the bone, so the change in length over that is that much. This is a very small strain, and so if you multiply by the length, so when you're standing on one leg, this is how much your bone compresses. Okay, so a 190 pound person standing on one leg, the bone compresses that much. That is the width of a hair. Okay, bones are hard and they compress only a hair's width when standing on one leg. All right, now let's go running. When you run, again, like I said, the impact forces are 7 times great. So the compression is about the diameter of a human hair when you stand on one leg. An increase in stress by a factor of 7 while running increases the compression by a factor of 7 to about 0.5 millimeter. So every time you run and your leg hits the floor, your bone compresses 0.5 millimeter. So that's what that number is. Okay? So again, but the stress is still only about 10% of the compressive strength. Okay? So if you want to break a bone, you probably have to jump from a height like that to the floor, okay, and not break your fall by rolling over and stuff like that. So, yeah. So osteoporosis is the weakening of these walls. Okay. Osteoporosis is a condition in which bones become more porous and thins the walls, making bones weaker. Okay. Thinning the wall is what makes the bones weaker. Okay. The osteoporosis is a metabolic bone disease of progressive loss of bone material. The microarchitecture of bone is constantly being recycled to maintain maximum strength. So the bone is being constantly remade to maintain strength. Okay. This recycling is facilitated by bone cells that resorb old bone and bone cells that build new bones. So the bone material is being absorbed and recast all the time, continuously. So your strength will be maintained as long as that balance is there. You're absorbing, and if you're not laying out enough material, then you're messing up the balance. So in a young person, the balance is always there. As you get older, okay, especially in women, as you get older, the homeostasis favors the cells that reabsorb the bone. So as you're getting older, you're absorbing more and not laying out as much, and so your bones are getting weaker. So that imbalance is what causes the bones to get weaker. Okay, and that's worse for women than men. It affects women more than men, as the hormones keep the bone resorption cells in check. Okay. All right, guys, so that finishes this chapter.